Hey students, welcome to another video with Accelerate Tutoring, and in today's video we're going to be going through the first module of the Year 12 Engineering Studies topic, which is civil structures. And in our previous videos we went through the first component, which is on the historical and societal influence, and today we're getting started on the mechanics of this topic, with the first topic being truss analysis. Now within truss analysis there are key things that you should be able to do, which is determine what the actions on a truss are, determine what the reaction values are, be able to analyze the pin joint trusses only, and then be able to solve using both method of joints and method of sections for trusses. Now, first of all, truss analysis is done on a truss bridge, which is a bridge whose load-bearing structure is made of interconnected triangular units forming a truss. Now, another way to think about what a truss is, it's a simply supported beam, typically horizontal truss supported at both ends, as you can see in this diagram over here, with one fixed support and one roller support. So here's our fixed joint on the right-hand side, and then here's our roller joint or movable support on the left-hand side. Now, for the two different types of joints, they both will have reaction forces being applied to account for the loads being applied to the truss externally. So we have F1, which is force 1 and force 2 being applied to the truss. So naturally, you would have reaction forces at the supports. Now, at a roller or movable support, there's only going to be one type of reaction force, which is vertically going upwards. And then at a fixed support, there's two types of forces. One is a vertical and one is a horizontal, which you can combine using basic Pythagoras and determine a overall reaction force at your fixed joint. Now, let's actually get into some questions to determine what reaction forces are. But overall, in terms of the types of questions that NESA can ask you, there are several different types. The first type is obviously finding the reaction forces. The next type of question is determining what the exact magnitude of a force in a specific member will be. And then the third type of question will be to determine the nature of the member in the truss itself. Now, there are two different types of natures that a member can be. Either it's going to be in compression or in tension. Now, typically, the external members of a truss, like the one highlighted in green, are generally in compression, and all the internal ones highlighted in yellow are in tension. Now, that's generally what happens, but you can determine that as well by solving for the force in each of the members itself and using your moments equation. If the magnitude is negative, then it's in compression. If it's positive, it's going to be in tension. Now, actually, let's get started into a question where we want to determine what the reaction forces are. Now, for all truss analysis questions, your three fundamental equations are the equilibrium of vertical forces is equal to 0, the equilibrium of horizontal forces is also equal to 0, and the equilibrium of moments is equal to 0. Those three key formulas is your bread and butter when it comes to truss analysis, and you'll be using them constantly for all different types of questions. So for this question, we're asked to find what the reaction forces are. So obviously we have a fixed joint over here and a roller joint over here. And as you can see, we will have a vertical and horizontal at the left fixed joint, whereas you'll only have a vertical at the roller joint. Now, typically with trusses, the step-by-step method you would take is you would first account for all the loads being externally applied. So we have a 30 kilonewton force being applied there and another one being applied there. Looking at this truss, it's equilateral triangles, so we know that the dimensions are all 4 meters. Now let's get started into determining our reaction forces. So the first thing we can do is account for the equilibrium of vertical forces equal to 0. Therefore, RLV plus RR, which are both going up, are equal to 30 kilonewtons plus 30 kilonewtons because they're both acting down. Therefore, together, they're equal to 60 kilonewtons. Now, applying the horizontal forces equilibrium is equal to 0, we know that the only horizontal force being applied is RLH. There's no external force being applied horizontally. Therefore, we can determine that force RLH is going to be equal to 0 kilonewtons. Now, to determine what exactly RR and RLV are, we apply moments about the fixed joint. So in this case, we can call the fixed point L. So we get moments about L should equal to 0. And then account for any direction, either clockwise or anti-clockwise. Usually we will take clockwise as positive. Now, a trick to help you determine on which side of the equation should the forces be applied for the moments equation, try drawing a circle continuously from each force. So RR will be going anti-clockwise, the 30 kilonewtons will be going clockwise, and this 30 kilonewtons will also be going clockwise. So now we can create a moments equation as 30 times 4 plus 30 times 8. So that's force times perpendicular distance, force times perpendicular distance is going to be equal to RR times 12. Therefore, RR is equal to 30 times 4 plus 30 times 8 all over 12. Putting this into our calculator, we should just get RR as 30 kilonewtons acting up. Now we can substitute back, and we should get RLV is equal to 60 minus 30, which is also 30 kilonewtons. Now, this is the full proper method of how to determine the reaction forces in a truss. Now, another faster way that you could solve this is by analyzing the truss itself. We can see that it is symmetrically loaded because, of course, RLH is equal to 0, so we can ignore it from this diagram. But looking at this truss, we know that it's symmetrically loaded because both of these forces are the exact same, and this truss, so we can draw a symmetrical line going straight through the center. So based off that, we now know that RLV and RR are both equal to the same thing, and they're both going to be equal to 30 kilonewtons going upwards. Now, let's look at this next example. In this example, we have forces acting down, vertically down, but we also have a force acting horizontally. Now, the first thing we can determine is that this is not symmetrically loaded, as we have this horizontal force being applied here. But in terms of determining the reaction forces, the steps are the exact same. We'll be using the same three fundamental equations, which is equilibrium of the vertical forces equal to 0, equilibrium of the horizontal forces equal to 0, and equilibrium of moments is also equal to 0. So now we know that RLV plus RR is going to be equal to 30 plus 30. So that's equal to 60 kilonewtons. Equilibrium of forces in the horizontal, we know that RLH will just be equal to the 20 kilonewtons being applied. Now we can apply our moments again about L is equal to 0. Now again, create those circles. So we know this is going clockwise, clockwise, anti-clockwise, and this 20 kilonewtons is also going to be going anti-clockwise. So now we can have our equation as 30 times 4 plus 30 times 8 is equal to RR times 12 plus 20 times D1. Now we want to determine what this perpendicular distance is. Now, the reason why it's 20 times D1 is because forces are acting along any straight point. So if this force is acting at this point, you can still imagine that it's being applied at this point here, going to the left. So this distance is still D1 about our moments point L over here. So to determine D1, we can just apply basic trig of Pythagoras. So we know that we have an equilateral triangle like so, with each side being 4 meters. And then this is 60. So we can just do simply D1 like so. So D1 is equal to square root of 4 squared minus 2 squared. So that's 8 minus 4. Sorry, that's going to be 16 minus 4. So that's equal to the square root of 12. That gives us 3.46 to 2 decimal places. So that's our D1. So now we can go back to our equation. RR is going to be equal to 30 times 4 plus 30 times 8 minus 20 times 3.46 all over 12. And that gives us RR as 24.23 kilonewtons. So now we can substitute this back and get RLV as 60 minus 24.23. And that gives us 35.77 kilonewtons. Now that we have RLV and RLH, you can determine what the overall resultant force will be. So our RLV is acting upwards, our RLH is acting to the right, so our resultant will be like so. And RL is just going to be equal to the square root of 35.77 squared plus 20 squared, and that gives us 40.98 kilonewtons. Now to determine the angle, that's just simple trig. So theta is equal to the tan inverse of RLV over RLH, and that gives us tan inverse of 35.77 over 20, and that's equal to 60.79 degrees. Now, these are all examples of finding the reaction forces. Now, say if we want to do the next step, which is of finding the forces in the members itself, to say with a truss like this is where you would be doing either method of sections or method of joints to find the nature in a specific member. So say if we wanted to solve this example over here, and we wanted to find the forces and nature of this member over here, and then let's say for part 2, we want to find this member. So what we will do is go through both method of sections and method of joints in terms of how to solve this. So the first step with any truss is to find the reaction forces. So we want to label them in. So we have RLV going up, RLH going to the right, and then we have RR going upwards. Now, by analyzing this, we know that there are no horizontal forces being applied, so we can just get rid of RLH because it's going to be equal to 0. So to solve for the reaction forces, we know that sum of vertical is equal to 0. Therefore, RLV plus RR is going to be equal to 12 plus 15 plus 10. That gives us 37 kilonewtons. Now we apply moments about point L. Again, clockwise. Here's where we can draw circles. This is going anti-clockwise, clockwise, clockwise, clockwise. Now we get 12 times 5. Now all these dimensions are 5 meters. Now for 15 and 10, 15, imagine it's going further down over here. Because again, a force can act along that same point infinitely. So imagine it's going down. So this distance is just going to be 2.5. And then for the 10, it's going to be 7.5. So in this case, our moment equation is 12 times 5 plus 15 times 2.5 plus 10 times 7.5 is equal to R times 10. So in this case, RR is equal to 12 times 5 plus 15 times 2.5 plus 10 times 7.5 all over 10. And that gives us our answer as 17.5 kilonewtons. And now we can substitute this back. The RLV is equal to 37 minus 17.5, which gives us 19.5 kilonewtons. So now we have our reaction forces for both the left fixed support and the right roller joint. So now let's actually determine what the force and nature of the green and the blue members are. Now for the green member, we'll be using method of joints, and for the blue member, we'll be using method of sections. So let's first go through method of joints for that green member. Now, method of joints is all based on concurrent force diagrams or 3-point force diagrams. So looking at this point over here, how method of joints works is you go through each point and draw free body diagrams and determine what the unknown forces are. So starting at this point L, we can draw that free body diagram as we have our point L over here. We have our reaction force going up, which we determined as 19.5 kilonewtons. We then have our unknown force acting that angle, and we know that angle to be 60 degrees. And then we have another unknown acting that way. So let's just label this as fx, and then this is fy, but we only want to know what fx is, so fy is not to our concern. Now, in this case, we want to determine what fx is. So the simplest thing that we will do is, again, apply our key fundamental formulas, but the only one that really we are interested in is the vertical force formula. Essentially, what we can do is we can break this force down into its sine and cos components since it's acting at an angle. So if we apply this, this is going to be fx sine 60, then fx cos 60. Now, since there is another unknown, fy, acting along the horizontal axis, we do not want to use our horizontal equilibrium is equal to 0 equation because we won't be able to determine what fx is through that formula. So instead, we're just going to be using our vertical equilibrium formula instead. So in this case, what we can do is say, because we know that the sum of forces is equal to 0, we therefore know that 19.5 is equal to fx sine 60, as they're the only two forces acting opposite to each other. Now, in this case, we initially said that it's acting upwards, but now because of the equilibrium equation, we know that it's going to be going the other way. So it's acting down instead. Now, since they're opposite to each other, therefore fx is equal to 19.5 over sine 60. And that gives us 22.52 kilonewtons. Now, looking at the arrowhead, when the arrow goes away from a point, that means it's in tension. But since in this case, we have determined that it's going towards the point, we know that this is going to be in compression. And that's what we have as our answer over here, 22.5 kilonewtons in compression. So that's how we do method of joints. You essentially just draw each point and then draw a force diagram like so and determine what the unknown forces are. Say, for example, we wanted to find what the force in nature in this member was using method of joints. All we would do is, again, draw that point. So say that's our point. We know that we have a force of 22.52 kilonewtons acting away, so in compression. And then we have, let's call this FA, what we want to determine. And then we have another unknown, let's call it FB. And we know this is 60 degrees, and that is also 60 degrees. Now, in this case, we have two unknowns, and we have one known over here. And if we wanted to determine FA, you do another similar thing of breaking each of the forces down. But if we look at this, we get this to be 60 degrees as well. And then we get 22.52 cos 60 acting that way. And then 22.52 sine 60 acting down. However, this FB is also going to be broken down. So we get FB cos 60 that way, and then FB sine 60 going down. So if we look at it in this case, we have too many unknowns. So we can't apply either of the equilibrium equations, which is vertical equals to 0 and sum of horizontal forces equal to 0. So in this case, for that point, method of joints will not be applicable since we have two unknowns. If we did want to use method of joints to determine it, the better approach rather than going straight up would be to go sideways. Now we do have another force here that I forgot to add, which was the 15 kilonewtons acting that way. So in this case, the step will probably be to determine what FB is equal to, and then after you've determined what FB is, then determine FA, but that is very long and complicated. So instead, we can use method of sections, which is done like so. Now, essentially how method of sections works is you have your truss and say this is the member we want to find the force and nature of. What we can do with method of sections is cut through our truss like so. Now, the rule for cutting through the truss is you can only go through a maximum of 3 members. So in this case, we have 1, 2, and 3 members we're going through. So say, for example, we wanted to find the force in this member here. So you can make a cut like so, but you're not allowed to make a cut going through, say, like that with the orange line, because you're going through 1, 2, 3, 4 members, which is not allowed. You can only go through a maximum of 3. So after you've made your cut like so, it's up to you to determine if you want to take the forces on the left-hand side of that cut or the right-hand side. So let's take the left. If we look at this member on the left, let's draw a free body diagram for it. We have our support over here. We have our LV acting up. We have our member like so. We have 15 kilonewtons acting this way. And then here's where we can have FA, we have FB, and then another force acting this way, and our cut is going through like so. And we know this as 22.52, but it won't be necessary in our equation itself. So let's take this diagram and analyze it. So looking at this diagram, we are only focused on FA, not on FB or FC. Now, the best way to go about solving this is, let's complete this drawing. And this is our truss triangle as shown. So what we can do to determine what FA is take moments about some point where FB and FC will cancel out, since they're also unknowns, but we do not want to overcomplicate our working out by having to solve them as well. So what we can do is, if we take moments about this point, which is just this point over here, both of these forces will cancel out, because remember, what are moments? It's force times perpendicular distance. And since the nature of both of these forces lies at this point, they will both cancel out. So simply, to determine what FA will be, let's call this point X. We take moments about point X, and obviously the equilibrium of moments about that point will equal to 0 in a clockwise direction. Then again, best to draw your circles. So FA is going to go clockwise. 15 kilonewtons is going to go anti-clockwise. RLV is going to go clockwise. So now we can write our equation as FA times, again, this perpendicular height, which is going to be D1. Let's just call it D1. Plus RLV times 5, because this distance over here is 5 meters. And then this is going to be equal to 15 times 2.5, because it's just half of it. So let's quickly find what D1 is. That's 5, that's 2.5, that's D1. Therefore, D1 is equal to the square root, 5 squared minus 2.5 squared. And that gives us 4.33 meters. Therefore, FA is equal to 15 times 2.5 minus RLV we determined as 19.5. So we get minus 19.5 times 5 all over D1, which we know as 4.33. And we get our answer as negative 13.9 kilonewtons. Now, since it's negative, that tells us that it's going to be 13.9 kilonewtons in compression. That is our answer that we can get. Now, in this case, it says 14.1, but that's just a rounding error. But other than that, this is how we go about doing method of sections. So whether you want to pick method of sections or method of joints, that's completely up to you. The question specifically tells you to pick one specific method. These are the 2 ways that we can go about solving it. So that's all for this video, going through truss analysis and ticking off all these subtopics of determining what the actions are, the reactions, pin joint truss. This is only method of joints and method of sections. Hope you like this video. Now stay tuned for a lot more mechanics-based videos for the entirety of engineering studies at HSC syllabus. If you enjoyed this video and the other videos on this channel, be sure to message us on our Instagram or email us at our email address to book yourself a lesson with Accelerate Tutoring.